I can say Sonu Solanki was the person.
Yeah. Sir,
Sonu
Sonu,
Solanki.
I think so. I will remove from here.
Okay.
Just a minute.
Just remove Sonu Solanki.
Okay, sir.
Okay, so we are continuing. So we can we were discussing about the computational need of
Hello. Hello.
is it I am audible?
Yeah, yes, sir. Now you are audible.
Okay, fine.
Okay.
Okay. So we are discussing about the computational need of vertical axis turbine when we are going for root cause analysis or inverse engineering design, particularly when we are talking about the engineering wind turbine farms. So that time we have to try to find out different locations suitable for vertical axis wind turbine installation, and without computational work we cannot identify in a large wind farm how to install the different vertical axis wind turbines at different locations. So for inverse engineering design is very important. We go for the computational work, and also when we do the aerodynamic analysis, or we want to know the root cause for a power improvement or a power reduction, we have no choice other than the computational work, unless you have a setup with laser, which you can do some flow visualization with the experimentation and can get some results and analyze that one and try to identify what is the root cause for a power reduction or power improvement. So both the experimental and computational are mutually important for any kind of vertical axis wind turbine research, and we are encourage both of the type of researcher as much as possible in the vertical axis wind turbine research. So if we go further, so now I will talk on the first of all on the small scale applications. So we'll see the Chauvinist type of vertical axis wind turbine. Basically, I worked on Chauvinist style vertical axis wind turbine for quite a long time, and the idea was, first of all, we thought about the starting capacity actually, because at a low winds region it's very important that you should have a wind turbine installed there, particularly on the rural side or above the buildings or communication towers. You should have a wind turbine design which can be efficiently converting your mechanical engine or kinetic energy to mechanical energy or electrical energy, and at the same time can start at very low speed. So the idea behind the study of style wind turbine was the starting capability at low wind speed. Then we identified some of the advantages, the simplicity in design, easy installation. Then obviously as a vertical axis wind turbine it is insensitive to wind directions. Application wise, we have some good applications of vertical Chauvinist type wind turbines. I remember I reviewed a paper in 2019 or 2018 in Italy. They were installing the Chauvinist type vertical axis wind turbine in the under the bridge. A 1 kilometer tunnel is there, and there was a regular passing of the cars. So to lighten the inside tunnel section, they want to have a alternative solution for the electricity. So they use Chauvinist technology there to light the vertical LED bulbs inside the tunnel. There is an application on US. My research partner, he installed the Chauvinist turbines on the communication towers. Although we all know that the Western countries, they are developed enough, but they are also having some situations where you will find some mobile towers or mobile communications, but you will not find the grid electricity that side. So to run those, you need the local electricity generation either by diesel operator generator or some other means. To support that communication tower, actually, he installed the Chauvinist turbines above the communication tower for local electricity generation. So, and recently I got some of the research collaborators who are installing the Chauvinist turbines on the rail tracks, just close to the rail tracks, to convert the energy from the rail movement. So there are some applications of Chauvinist, and they are also useful on the starting torque producer for many others vertical axis wind turbines. So While we are studying about the vertical chauvinist type vertical wind turbine, we actually tested a variety of designs for chauvinist type turbines, starting from the same design which was presented in 1929 by S.J. Chauvinius, a Finnish engineer. From that time, no, we have received a number of designs for chauvinist turbines. Well, particularly the Benesch and Batch type in 1970s and 80s. Those designs are very popular, and based on all the different designs, actually we studied the blade arcs, the overlap distance, the flow physics, and we optimized the chauvinist design and obtain a power coefficient of around 0.31, means around 30 to 31% efficiency, considering the wind tunnel Bloch-List factors and other things. So that was the wind tunnel, which was in IIT Guwahati, and after that, no, we did lots of numerical simulations in IIT Guwahati, also initially in France in École Saint-Laurent also. So basically, the idea behind numerical simulation, we want to do a root cause analysis. So root cause analysis, particularly for the root cause analysis, we want to see the different forces those are acting and why the performance is improved with the new design or optimized design. So we went back to very general classification of a moment, that is force into perpendicular distance. So that force into perpendicular distance for each plate, we try to identify what is the force into perpendicular distance due to the advancing blade, due to the returning blade. Means advancing blade for chauvinist design is which is moving with the incoming wind flow in a positive direction, and returning blade which is coming back. So we have to analyze both the blades and try to identify what is the root cause. So for that one, we try to identify the force first, and then we try to identify the center of that force. We look at the pressure force there. So we try to identify that center of pressure on each of the blade because of the drag and lift. So, okay, so this is the screen of the grid. Okay, so this is the screen of the grid, and we can see here we used actually polyhedral mesh in star CCM, which is almost a similar kind of software as ANSYS. You will see ANSYS Fluent or ANSYS CFX. It's a similar kind of mesh, but we have a polyhedral mesh there, so we have better skewness or a better transition of various parameters to obtain a better convergence and to get an effective value. So for that one, we used Star CCM. We run this one in a server PC, and we ran actually a number of simulations. So during the simulation, we did some grid independence test, Y convergence. Those are the basics, fundamentals of the CFD, and we try to do our validation case with the different experimental results because we had not measured the lift and drag during our experimentation. So we identify some other experiments for drift and drag and lift comparisons, and quite satisfactory comparison was achieved. And then we try to understand the different forces in terms of drag and lift, how those are acting, and how actually new blade contributing to the power. So the long handle of the new blade, we have seen actually that returning blade, where in the conventional design normally gives a negative power to the total conversion. However, the handle which is for use for the new blade is actually giving some positive power or positive drag to the total power. Then we have also studied the lift, and we obtained that how lift is actually contributing and how the lift coefficients varied. So we tested for different wind speeds, for different speed ratios, and we obtained very similar kind of results. With the advances of Reynolds number, the power coefficient is little bit improved, and those things we observed. Interestingly, what I want to show here, interestingly, the effect of center of pressure was more important, because we want to identify not only the force, why the only force was responsible, or there is something else. We identified that with the new design, actually center of pressure is shifted for the lift or for the drag actually from the center of rotation. So that means that perpendicular distance is actually increased, and that was actually main reason behind the power improvement. Not only the forces we improved, but the perpendicular distance also we improved. So we analyze the flow, in a different way according to the stall, and different conditions. So I'm not going to explain the fluid dynamics here. And for lift also, we also try to notice here what are the center of pressure for lift force, how it is changed. You can see in this figure very easily now at the XP, which is nothing but the center of distance between center of lift and center of rotation, it is increased. And from the left side diagram, we can see that how actually suction function on the advancing blade. Advancing blade, I can say it is this blade. So how actually suction function in the advancing blade, we can see clearly that with the new blade, this suction has been improved. This suction actually responsible for your high lift force on the new blade. And with the acting point of this section, or you can say center of pressure, actually responsible for this total improvement of power. So with this analysis, right, we actually then calculated the total moment in terms of average moment, and then from that we calculated the power coefficient. Then we analyzed the different components, flow physics, how the vortices is moving with and without shaft. Because when we go for the design of a vertical twin turbine, generally we do the simulation without considering the shaft. That is a very common practice in simulation industry for vertical twin turbine. We are not considering the shaft, so we try to see how it is implemented for the new design as well as for conventional design. If we consider, if we don't consider, we try to see that one. Because when we go for implementation, that time actually we have to install a shaft. Without shaft, you cannot put in 1 meter size of turbine. So that was very important. So we tried to do a shaft analysis with the help of FFT, and we understood that for the conventional semicircular design, actually shaft is contributing to a negative way on the total power production. So it is generating some kind of vibration in the near about zone of shaft, which is creating some vortices which are disturbed, which are into the flow through the overlap. Traditionally, the overlap flow is responsible for a positive contribution to the power, but when you install the shaft at that time, actually this positive effect is converted into a negative effect because of that noise you can see in these diagrams. So because of those scenarios, if we zoom a particular picture, this FFT has been taken from the moment coefficients of turbine. So if you see those FFT, you can easily identify that in a semicircular turbine, the disturbances caused by the shaft is very significant, and which is when you predict a turbine performance without shaft for a semicircular design, you will get maybe an efficiency of 30%, whereas critical point of view, the efficiency will not that much high. It may be end up with 18% or 20%. So that is a very good reason, or we identified that is the possibility for the power reduction for the semicircular turbine. The new design, because of long handle, the vortices was caused by the shaft, it is actually mitigated within before it reaching the returning blade suction side. So that means the negative effect is actually not significant in the new blade rather than in the conventional blade. So that was a very interesting finding from that research, and that was presented in a conference in Italy, and well appreciated that one. After that, actually we done some research on the Darrius-Star vertical twin turbine also. That is particularly focused on some application, that is cooling tower exhaust application. We are also doing some souvenirs design also for cooling tower exhaust application. And one of our research partner in University Malaysia, University Malaya, you can see their experimental setup in this video. So is it visible this side also? I think yes. No, yes. Okay. So this is an experimental setup in University Malaya. So you can see here, this is the exhaust system coming out from the cooling tower. and the souvenirs combined with a egg beater, that is turbine installed in the list, and the efficiency was recorded around 14 to 15%. So which we thought a very low actually comparatively what was expected efficiency. So we submitted again a government project based on this combined turbine, and then we proposed that if we install a Darius turbine instead of a combined Souvenirs Darius turbine, maybe the power conversion can be much more increased, or we use some counter rotating Souvenirs turbine. Sorry, maybe the power efficiency will be much increased. So based on that, we submitted some projects for the government funding, and luckily we obtained the government funding for the ongoing research. And we are now in Malaysia also. We are conducting some research on the cooling tower exhaust systems. And here are some 3D simulations results. We started some calculations on the numerical simulation first, and then we fabricated. We actually done these numerical simulations on the cooling tower of using the 3D calculations. So for one simulation, it takes around 1.5 day time for a particular 1 RPM, 1 TSR case. Our computational domain, and we conducted, based on these boundary conditions, or you can say initial conditions, we calculated the forces and power coefficients there. So initially, as a process of computational fluid dynamics, we did the grid study. So without turbine, with turbine, we did the grid conversion study by taking some point probes in the computational domain, and taken around 5.6 million cells for the final design for a satisfactory computational results. And based on that, actually we studied initially the effect of aspect ratio if we place at various type of turbine on the cooling tower applications. Recently we have some more research going on the Darius as well as on the Souvenirs type turbine on the multi-rotating turbine placed in the cooling tower exhaust. So our students are getting some good results, and we'll see maybe next few months we'll communicate some results for the publications. And from these results and measure highlights where we obtain the aspect ratio contribution to the power. We seen that aspect ratio is very important when we are considering the cooling tower exhaust systems, and we have to obtain actually the good velocity regions, and we have to place the aspect ratio according to good velocity regions. And the effect of guide vanes and diffusers, multi-turbine interactions, other cross-flow wind turbines are still going on, and experiments will be conducted on similar conditions. So that is the ongoing projects. Some other ongoing projects I would like to share with you. That is a particle axis wind turbine with pitch control. That project is with IFA, and we have actually multiple collaborators in this project, starting from industry and different laboratory and university. So till now, actually there is no particle axis wind turbine installed on the research stage, and with the pitch control, actually I have not found any particle axis wind turbine in practice. Now, why we are looking at particle axis wind turbine? Particularly, we want to see how the particle axis wind turbine can be, or its performance can be improved with the pitch control mechanism. Because all we know that when we start the particle axis wind turbine, or particularly the straight bladed, up to around 4 to 5 meters per second, it is not even starting. So that is a problem. Now, with that thought, we started the simulations. So what was the benefits of thinking particle axis wind turbine? That the gravity center was low, is low for the floater conditions for the particle axis wind turbine. So floater requirement or floater investment is much more required, much more reduced. Then the particle axis wind turbine can be function as in the large inclination also. Then actually for when you talk about the multi-turbine installation in a wind farm in an offshore condition, we can install actually a number of particle axis wind turbine in a closed area as compared to the horizontal axis windmills. So the power production per area will be much improved. Then we actually there was an ongoing project also of UFI with a 6 spin float. which of 6 megawatt vertical axis wind turbine with pitch blades. So the contributors are IFE, the MIO, then French government. So all are contributing. So you can see here how actually pitch control will affect. Basically, when we pitch the blade, we will change the angle of attack, and because of this angle of attack, the lift force will be changed or improved. And because of the force improvement, you will the tangential component of the force will improve, which will at the end increase the resultant force, and that is the force which is creating the turbine torque. So at the end, with the pitch control, you can improve the total power performance. We can think about the good self-starting for with the pitch control, as well as we can think about the how to stop or slow down the turbine. If we optimize that pitch angles for the stopping condition, we can stop when there is a requirement of the maintenance, or when we stop a turbine at because of some unwanted conditions. So for that one, maybe in some conditions we have to stop the turbine. So we have to find a better low pitch low how to stop a turbine. So for that target also we contributed to research on the pitch control mechanism. There are some research papers on the pitching of vertical wind turbine. However, for those all are on the university scale of research, and mostly on the small turbines, and the mostly solidity ratio. So we all know that for vertical wind turbines, the smallest solidity contributing to higher power. So again, because of structural issue, we have to consider optimization of solidity and structural strengths. So after focusing all those points, we aim for the low solidity ratio with higher turbine blades to test a turbine to get some conclusion of the pitch loss. So that was the wind tunnel, or we can say wind water tunnel, because that particular wind tunnel has been used for not only for wind turbine but also for the wave energy experimentation. So in this particular setup, the different wave heights and wave frequencies, wave strengths, those also measured, as well as floating type different turbines, and then without water we test also the turbine. So this is a multi-purpose wind tunnel having a dimension of 2.5 into 3 meter and of 40 meter length. It's quite big. So I used to go inside the tunnel and do the experimentation while it required that time. So this is now some of the pictures from those wind tunnel. You can see here some testing on the horizontal floating type horizontal wind turbines, and there are some vertical wind turbines installed in the capacity. So we tested some of the designs. We started with some basic calculation with exploil and tube blade for the blade design and the solidity ratio calculation, and we obtained a aerofoil. We cannot say it's obtained because it's already existing aerofoil. We obtained the design with that aerofoil, but with solidity ratio of 0.17. But interestingly, till now, as that Selig 1046 depth profile, there is no evidence of experiments for the lift and drag aerodynamic forces experiments, and there is no concrete evidences of that. So we conducted actually a rigorous testing on the S1046 for measuring the different drag and lift forces and at different angle of attacks, starting from 0 to 180 degree. And after that, we fabricated the vertical axis wind turbine using 3D printing and different control mechanisms using servo motors. So we installed the whole wind turbine. You can see my face here with the turbine blades. So those are carbon blades, and the structure was made of 3D printing. So those blades we installed in the turbine and using the pitch control. So you can see in the video, right? And there is a pitch control movement using servo motors. So those in the capacity, and with the help of a sensor we used to measure the torque of the turbine. So in this particular video, you can see the turbine is rotating inside the wind tunnel. A different speed ratio we tested the turbine, and with implementing some pitch low. So you can see in the video that if we implement the pitch low, actually the turbine rotational speed is also changing. So the mechanism actually involved there was a computer control core And that control code we used to send the command in the one Adreno TNC card, and that card is installed in that turbine section, and which is giving commands to the servo motors to control the arm movements. So that was the basic fundamental thing. And then we actually go to the next level, where we wanted to implement the TSR effect, means the rotational effect with combination of the incoming wind speed. That effect in the control pitch control servo motor. So what we did, we actually installed some sensors for velocity measurements. We installed some sensor for the rotational measurements. We giving the same we feedback this information to the computer. The computer take the data for TSR, the angular speed, and the incoming wind speed, and based on that, it prepares a control law which is sent back to the servo motors again to control the good pitch for the blades. So that was the loop. While we see the results for actually for rotational speed, you can see without pitch, actually we are getting at 5 meters per second. The rotational speed were very low. Where when we did the pitch control, the rotational speed we got a good amount, but however it was small because it was the initial phase of experiments. Then we tested actually the starting control of the vertical extrusion turbine, and you can see here with the pitch control. If you see the blue line with the pitch control, the starting is obtained almost at 1 meter per second for all azimuthal angles. Means we fix the blade at certain angle. At all angular positions, we can obtain the starting of vertical extrusion turbine with the pitch control at 1 meter per second. Whereas if we don't implement the pitch control, we can see here at different angle of attack, the starting of the low pitch control turbine is different. So at certain angle of attack, it is starting at 40 meter at 5 meter per second. At certain angle attack, it is starting at around 3.5 or 4 meter per second. We can see how the starting actual capability has been implemented, pitch control implementation. And then we have tested actually also the function for the beta, means how to stop the turbine. You can see here, if we closely look at this video, usually rotating when we implement the beta, then it stopped at after 1 or 2 rotation. So at the end, now we are still improving our pitching law to implement the TSR and incoming speed and rotational speed. So with 12 parameters equation, we are taking input and we are implementing pitch laws in the turbine for acquiring a higher and higher performance coefficient and good stopping conditions. So as you can see here, we conducted around in 1 hour we conducted around 30 runs and taking information to the Dakota code. Dakota is a open source code for optimization. I hope all of you know that thing. And then using that optimization toolbox, we are trying to optimizing the pitch law for the turbine. You can see here different pitch laws that we have tried for different angle of attack for different TSRs. So those actually will be inserted into the code into the servo motors, and you can see it is a 4 meter per second and with and without pitch. So if I drag this video at the beginning, so this is without pitch, and then when we implement the pitch, this turbine rotation has been changed, and you can see how the turbine started. So that is implementation of pitch control in the various type of vertical extrusion turbine. However, still experiments are going on, and we are trying to maximize the performance with the help of this pitch control. So that is another form of vertical extrusion turbine implementation. So we have seen that different ways of application. One is based on a small scale application. One is based on to handle the to recover the energy from the exhaust system, and another one is on large scale. Basically, it's a small scale model, but our target is to implement it in a large scale for offshore floating conditions. So that's my presentation. So maybe now based on presentation to have some healthy discussion.
Thank you. Thank you very much, sir. AP sir. AP sir. We
Yes, yes, yes.
we have only 8 minutes.
Thank you very much, Dr. Swantara, for giving a nice presentation. Now, I would like to request all the participants, if anyone having a questions regarding the same, either they can post or can directly ask the question from the Dr. Roy.
I think we can open the chat option also. Is it possible? Yeah. Okay.
Yeah, no, so.
AP sir, few question in the chat box, so you can ask from there.
In the chat option, actually, there is a question from
Gaurav Patel.
Gaurav Patel. How to store that energy? Actually, energy is related with the energy storage system. Definitely, we have to go for a feasible energy storage device for to store the energy. Although my research is not on the energy storage side, but I can say we have to implement the for any kind of energy solution, particularly on the renewable energy side. We have to think about the energy storage devices, because all the different kinds of renewable energies, you will always find whether it's a solar, it's a wave, or it's a wind. We have to consider the energy storage system.
Hello.
Yes, Arvind, you can ask.
Santosh sir, you can ask.
Hello.
Hello. Good afternoon, sir. This is Santosh Rathore from Mechanical Department. Actually, my question is that the BETS has derived an equation for maximum wind energy may be produced 59.2%. So, is it possible to increase this percentage?
Actually, if you say that batch limit, right? Batch limit was developed based on the disk actuator theory, and it is based on particularly for the horizontal axis wind turbines.
Yes, sir.
And it is not really suitable for the vertical axis wind turbine. Although the vertical axis wind turbine, there is no theoretical maximum limit, or there is a law established which is for vertical axis wind turbines. But definitely the laws, batch limit controls, it is particularly suitable for horizontal axis wind turbines only. So if we obtain a higher output, although we have not obtained till now, but if we obtain, that is not a surprise.
Okay, sir.
Hello. Good evening, sir. This is Arvind Lingwal. Sir, I want to know that you collect the information. Can you explain that how we can collect information that set up to computer through Arduino?
Actually, that is part of my electronic. I have not on that division particularly, the electronic component side. But however, I can give you an overview of this information. So basically,
Yes,
we had a
actually,
code running on the MATLAB, and that MATLAB actually was connected with the Arduino code, and that Arduino code was counting we inputted all the mathematical equation inside the MATLAB, and we are connecting the Arduino codes also for those servo motors, and whatever commands we are receiving, that commands we are passing from this MATLAB program to the Arduino. So that was one of the electronic student that side. He was controlling that part. But I can see that it is possible. But I cannot give you all the details basically of how to control the Arduino with the help of servo motors.
Thank you, sir.
Yeah, I am not a control person actually. So if any questions coming to me on the control side, maybe I am not the suitable guy to answer that one. But definitely you can ask maybe later on. I can consult. You can email me. I can email my counterpart, my collaborators. Maybe we can find some solutions for
Yes,
that.
thank you, sir.
Any other question from the participant side? Okay, so just we are going to end the session. Before that, I would like to invite Dr. Lokesh Kumar Boriwal to say the vote of thanks. Dr. Lokesh Boriwal, sir.
Thank you, officer. I would like to say thank you very, very much from the Department of Mechanical Engineering, SIRT Sage University, to the Dr. Sukanta Roy, sir, to deliver the and also explain deeply and also share with us the recent research in the area of the vertical axis wind turbine for renewable energy generation. Also, definitely, sir, some of the our faculty member also looking to complete their PhD. Definitely, they will be joined in such very very interesting area for the energy purpose. And heartily thank you to share your valuable time with us and give us the time. And also thanks from the all the faculty member of the mechanism department. Heartily thank you very much, sir.
Thank you for organizing
Now
this
I
event.
hand over
And
to Adish, sir.
also very grateful. And in the future, maybe if some of the colleagues, as Dr. Lokesh said, if some of the colleagues are interested, maybe we can have some collaborations also on the research component. So it will be a great. If anywhere I can
Yes, sir.
contribute, let me know also. Maybe we can think of research also in future.
Sure, Doctor. My colleagues are too much interested. 100%, I will get some collaboration with the Cotton University and Sage University, and we will do some kind of further research in the field of the renewable energy related to the wind turbines. Once again, thank you very much on the behalf of the Sage University, the management, engineer Agarwal sir, chairperson ma'am, and executive director Shivani ma'am and such ma'am, and vice chancellor sir, pro vice chancellor sir, and from the head of the department, I would like to once again thank you for very much for having such a nice information related to the wind turbine in field of renewable energy. Thank you very much, sir.
Thank you.
Thank you, sir.